Any ideas? What transformation could we use to map ABCD onto EFGH there? Steven, you got an answer?
I think,
What do you say?
not sure if this is right, but I said transition down and right. Well, transition down 4 and right 4.
Down 4 and right 4. Translation. Okay, great. Yes. What kind of clued you in there maybe that it was going to be a translation?
Well, it looked the same to me, so it wasn't like a dilation, and it wasn't a rotation, because if it was a rotation, then D and B would G and F and C and B would be closer to each other.
Okay. So maybe like different kind of positions for the points. The points, yeah. So the orientation is still like the exact same there. So yeah, exactly. And so a translation. And you said it was down 4 and right 4? 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. Yeah. I'm going to use the vector or like a vector here. So -4. Nope. 4, -4. There we go. Okay, so that's right 4 and then down 4. So then what does this confirm about these two planters? What can we say then?
I didn't say anything for that.
Okay. So if you look up here, we're trying to confirm congruence. So since we can map those things right on top of one another, we can say that these two shapes are what? Congruent, right. Okay. And so this confirms and then we're going to write the congruence statement here, okay? So I'm going to use the alphabetic order here. A, B, C, D, okay, is congruent to, using the congruent symbol there. Okay, so I'm going to say A, B, C, D is congruent to, and then can I just list any of these 4 letters in any order I want here? No, okay, so then what's the order I must list this in? Brandon, what do you say? E, F, G, H. Okay, exactly right. Because A in the original or pre-image, A corresponds to what in the image? E. And B to F, and C to G, and D to H. Okay? So that congruent statement, right, is an important statement to make, and you have to be accurate with it. Okay? So don't just willy-nilly, name things. Now, did I have to name the original shape? Did I have to name it A, B, C, D? Do I have to? No. Normally, when you're like seeing a problem, normally it's in alphabetical order, but you don't have to. You could have just easily said here D, C, B, A. If I named it D, C, B, A, then I would have named this one H, G, F, E. Jenny, question? I guess so. You could use that still if you wanted to because of the directions. But I wouldn't say you were wrong if you listed in a different order here, but then use that same different order here. That's okay. Because again, the congruence is more about a relationship for the thing. So, okay, good. All right, letter B. We have now pools, JKLM and NPQR. Okay, and then fold your paper so that JKLM is mapped onto pool NPQR. Describe the transformation. So what kind of transformation here would map these two onto one another? What kind of transformation is that? Jake? Right, so it's definitely a reflection. The y equals x part, it's a little bit trickier here because we don't really have like an x-axis or y-axis, but it's definitely, yeah, it's a reflection. Okay, I'm just going to say over a diagonal line for right now because, again, we don't really know coordinates or anything over here to say that y is equal to x. Okay, and so then, Jake, what does that confirm about these two pools? They're congruent, yes. And so this confirms. Do you want to give us our congruent statement here, Jake? So, like, what is congruent to what here?
Sure. JKLM is congruent to NPQR.
Yeah, is congruent to NPQR, just like that. Okay? So this is helpful. They already gave the names in the right order for us and stuff. All right, letter C, determine whether the lawns are congruent. So these now have these triangular lawns. Is there a rigid transformation? Is there a rigid transformation that maps triangle LMN to triangle DEF? What do we say here? So I see some no's. So Aubrey?
I said
No.
no because the size of the two figures changes.
Exactly right. No, the size of the triangles are not the same. The sizes of the triangles are not the same. Okay, very good. So what does this confirm about the lawn? The lawns are, what would we say? Anybody? Jay? Not congruent. Exactly right. The lawns are not congruent. Okay. Super simple stuff, right? Super simple stuff here. Okay. But this is going to lead directly into some things we'll be talking about next unit too. So that's why we're kind of trying to bridge that from talking about rigid motion transformations to then congruence. So it's kind of similar to what we were talking about, stuff already here. How do the sizes of the pairs of figures help determine if they are congruent? What do you say? How do the sizes of the pairs of figures here help to determine if they are congruent? So Avery, what do you say?
If the figures, at least in this case, are the same size, then they are congruent, and if they weren't, they weren't congruent.
Okay, so yes. How do the sizes of the pairs of figures help determine if they're congruent? If the sizes are different, right, like Aubrey noticed in letter C, if the sizes are different, okay, the figures cannot be congruent. Okay. If the sizes are the same, I'm going to put if the sizes and then in parentheses and shapes are the same, they are congruent. The figures are congruent. Okay. I know it's weird to specify size and shape, kind of trying to make those two things seem different, because really I don't know anyone that would look at two different shapes and say they're still the same size. I mean, I guess that could be a thing, right? Someone, I guess I could draw, a square and then draw a triangle, and I'd be like, are these two shapes the same size? And maybe people might say yes, and then I could say, are these two shapes the same size? And you might be like, no, because that triangle is bigger than that square. So I could see that maybe, why we need to specify. But also it's if they're different shapes, we would never say that they're the same size exactly, right? Because they're different things we're talking about. Anyway, that's part of congruence though. Same size and same shape. Okay. So turn the page here and let's take a look at some of this stuff. So again, remember that definition of congruence, two plane figures are congruent if and only if one can be obtained from the other by a sequence of rigid motions. Okay, so that's an important, kind of understanding of congruence there. We call something congruent, we call a pair of things congruent if one can be obtained from the other by a sequence of rigid motion transformations. Okay? So looking here then at the next page, page 128, okay, we're going to be looking at determining if figures are congruent. Okay, we have an example done for us here. So use the definition of congruence. That's that definition that says, when you have a pair of objects, they're congruent if and only if you can obtain one from the other by a sequence of rigid motion transformations. Okay, so looking at this, right, we see, okay, here's our pair of figures. Do they appear to be congruent? Yes. Okay. What transformation could we use, or transformations could we use to map them onto each other? Anybody? Reflection over the y-axis. Exactly right. And that's all we need. Is a reflection a rigid motion? Yes. And so will the shapes be congruent? Yes. Okay. You further could give the coordinate notation if you wanted to, but it's not necessary. Okay. It's not necessary there. All right. Letter B. The two figures in letter B here appear to be the same or different? The same. Okay? You can map triangle ABC to triangle XYZ by what? Daniel?
Rotate counterclockwise 90 degrees.
Rotation, 90 degrees. I'm going to use a CCW there. In the coordinate plane, remember also, if you say just 90 degrees, it'll be assumed to be counterclockwise too, so it's not necessary to say counterclockwise if you don't want to, but it's okay if you do. It's okay. And I guess rotation 90 degrees counterclockwise about the origin 0, 0. Again, we really should specify our center of rotation there. Okay? This is or is not a rigid motion. Avery?
It is.
It is.
Also, would
Yeah.
it be just counterclockwise or would it be clockwise?
We're going from ABC to triangle XYZ. Yeah, so that's important to think about too. Now, granted, could you say the same thing? Like, could you say, would I be okay with you saying rotation 90 degree clockwise? Absolutely. Because it doesn't matter whether I'm mapping this to this or this to this. It won't matter because we're trying to just prove congruence here. Granted, the directions kind of lead us, we're taking triangle ABC to triangle XYZ. But in general, if you're just given this picture and said, ask proof congruence, if you said rotate 90 degrees clockwise, rotate XYZ 90 degrees clockwise, that'd be fine too. Okay? So little subtlety there. The coordinate notation for the rotation is XY arrow what? We haven't talked a whole lot about this, trying to come up with the coordinate notation here. Madison? You say x negative y? Aubrey, what do you say? Negative yx. Okay, so we got x negative y. We say negative yx. All right. Anyone want to offer something else? So, how can we maybe figure this out? Jackson? You say y negative x now. Okay, so we have three options here. How can we maybe figure this out? Madison? So C, okay, C, our original point here, I'll put that underneath this original. C has coordinates, what are C's coordinates here? Now be careful. Look at the scale on your axis. And I don't like that they do this sometimes. They change the scale up on us, but it's actually 4, negative 2, isn't it? So we're taking the point 4, negative 2, and C is supposed to match to what point? Z, which has coordinates 2, 4. Okay, so how do our points change here? How do our points change? Avery, go ahead.
It's negative y.
So right, our y coordinate here changes to a y coordinate here, but it changes from negative 2 to positive 2. So yeah, we need a negative y. And then our x coordinate here, 4, becomes the y coordinate, but it stays the same sign. So it looks like it's negative yx. So there it is right there. It was that one. Okay. So, and that's something, a strategy you can use in general, right? If you're not sure about the coordinate notation for something, do exactly what we just did right there. Pick a point and its image and then see if you can figure out what the coordinate notation would be there. Okay? You don't need to memorize them if you don't want to. Alrighty? So, let's go ahead and have you try number 3. Okay? Try number 3, please. On your own, try number 3 there. Okay? So use the definition of congruence to decide whether the two figures are congruent. Explain your answer. So explain your answer. Be ready to explain your answer. right? You can tell exactly what kind of transformation would map. That's great, but for an extra challenge, see if you can come up with a coordinate notation that would take each of those vertices to their image. That's a trickier thing to do. You have to explain why they are congruent. See if you want the coordinate notation there. It's tricky. It's tricky. Okay. So, let's go to somebody here. Let me pick somebody at random. Right, how about Eli? So Eli, for number 3 there, what transformation could we use to determine whether these two figures are congruent?
I said it was a reflection over the line x equals 3.
Okay, or you mean -3?
Yeah.
Yeah, great. Okay, reflection over x equals -3. Well done there. Okay, so we can talk about reflecting over things that are not the x or y axis in the coordinate plane there. Okay, was anyone able to come up with the coordinate notation here that would be able to transform the different points? All right, so in other words, if we have a point x, y, and let's talk about transforming, oh goodness, I think I did mine. I think it'll still work either way. So, -4 plus 3, -1, +1, -2, yeah. So, any ideas here at Madison?
I said a half x, y.
1/2 x and then comma y.
Yeah.
Okay, so let's see here. So the -2x coordinate here, half of that. Oh, you did from j to x.
Yeah.
Okay, my apologies. So negative 4, half of that would give us negative 2. Okay, so that would be, so let's see here. So you said 1/2 x, and then you said y, right? Okay, so certainly for j, if we took, let's see, what is that? Negative 4, negative 6. Yep, so the y coordinate there would still be negative 6. That's right. Half of negative 4 would be negative 2, and so yeah, that would work. So that would get us to x. Let's take a look at k. So let's see here. K's coordinates are negative 10 and then negative 2. Okay, and so that's supposed to go to y. Okay, half of negative 10 though is negative 5, and we need y to be a positive 4. But the y coordinates are still right. Right? The y coordinates are still right. So it looks like maybe that 1/2 x isn't going to be true, but the y will be just y though, right? Same thing here. L is going to have the same y coordinate as z there. So it will be the same y. But again, if we do 1/2 that negative 8, it's going to not give us a positive 2, we get a negative 4. So not quite. Avery, idea?
This is just an idea, but is it negative x minus 3?
Negative x minus 3. Okay, so let's check there. So let me see here. I'm going to have to write this one down here.
Oh wait, no, that didn't work. Sorry, I
Yeah.
thought it was 3.
So why did you do negative x minus 3? What was your thinking there behind that one?
Well, I knew that the relationship was it was going to be the distance from the x coordinate to negative 3. And then you just add, so you add the distance
Okay.
to 3.
Okay.
But I couldn't figure out how to notate that.
So let me kind of talk you through here, so, like a way that I was trying to think about it that I've seen before in the past. Okay, so we traditionally in the coordinate plane do not do reflections over lines other than like the y-axis or the x-axis, right? Or like line y equals x or y equals negative x. So what if we took this and imagine taking this transformation and let's shift it so that the y-axis is our line of reflection. So in order to shift these shapes so that my y-axis is the line of reflection, how do we need to shift it? To the right, 3, right? And so I'm going to now take my x, I'm going to add 3 to it. Okay, y is going to stay the same. So now I've taken my original shapes here, and I've moved them right 3 so that my y-axis is now my center, my line of reflection.
Okay, I think I've just figured it out.
Okay?
Negative x minus 6.
So essentially, yes. So you combine it all together. Let me take it into the pieces, and then yes, that is exactly what it would be. So now at this point, okay, I've shifted everything over. What's the notation for reflecting something over the y-axis? The y values don't change, but what happens to the x values? They're opposites, right? So let's take this thing that we shifted right 3 and now make it the opposite. We've now done the reflection, but the line of reflection is still at the y-axis. I need to move it back to where it was. How do I move it back to where it was? I need to shift it which direction? Back left 3. So we'll do minus 3. Okay. If you distribute the minus sign, we'll get negative x minus 3, but minus another 3, negative x minus 6. And there would be the transformation for it right there. Okay? All right. Don't fret, okay, if I lost you like 5 minutes ago when I started describing this, all right? But I think I'm going to try and look at some of the more of this tomorrow, okay? To get, just get some practice with it and stuff like that, okay, to see it. But yeah, that's the idea. So good job there, okay? If you followed along with that, good job, okay? That's the idea. All right. So of course then, sometimes, right, to describe two things as being congruent, we all want to be able to describe, sometimes we need to use more than one transformation, okay? There may be a sequence that we need, of rigid motions that we need in order to map one to the other, Okay, so for example here, for A and B, right, we're told the figures are congruent, and we're supposed to find a sequence of rigid motions that maps one figure to the other, and then give coordinate notation for the transformations you use. Now you'll notice they don't have us doing the coordinate notation all at once. They have you do it once and then like the 1 and 2, right? So they don't have you do it all at once. Okay, so obviously there's some choice here, right, about how you do it. For example, in this case, they have us rotate first and then translate. Do we have to follow that order? Do we have to rotate 180 degrees around the origin and then do a horizontal translation? Or is there something else we could do here? Do we have to follow this order? You say you have to follow the order? Okay. Can anyone think of a different order we could do? Yeah, Stephen, what do you say?
Maybe you like reflect ABC by the x and y axis.
Okay, so if we reflect ABC by the y and then x axis, that would put it like right, like it would put it close there, and I think we still have to translate it like 1 over, something like that. But yes, exactly. So alternatives here, right? You don't need to necessarily follow what they say. Yes, there's more than one way to do it. Okay, so you take as many steps as you want. Now, obviously, for the sake of your time, you're going to want to try and do as few as you can. Okay. How about letter B here? How could we do letter B? And again, be careful here. I know it's weird that like the side of our shape is like in a halfway point. Remember, we're counting by 2, so really this is all at 1 and stuff like that. So ideas here, how can we map A, B, C, D to JKLM? So we want to take this shape to this shape right here. How can we get this one to this one? What could we do? Yeah, Emma?
Reflect ABCD
Over.
the y-axis.
Okay.
Translate it down to
Reflect, and then you said translate. Oh, right, it said reflect. Oh, okay, never mind, I see. Reflect about y-axis followed by a translation. Okay, great. Yeah, okay. So for the reflection about the y-axis, can you give me the coordinate notation for what that would be for a reflection of the y-axis there? It would take our x, y, and make them So for example,
your x would be 2. Yeah.
so the x for like, which point are you looking at? Maybe let's pick a point, like A.
Yeah.
So A would have what's A's coordinates right now?
3, 4.
3, 4. A would reflect over to here.
-3.
Yeah. So 3, 4 became -3, 4, and so x, y will become, for that reflection, if that's our x and that's our y, it becomes -x and still y. Do you see that? Okay there, Emma? Yeah. Okay. You weren't going to say something there?
No.
Okay. So there's reflection. Okay, and then that'll take us to, let's see here. So if we do that real quick. And there. And then B is right there. And then C is right there. And then D. Right there. Okay. And then with the translation. Okay. Someone help us. I mean, Emma, do you want to do the translation too?
Sure.
So how would we want to translate that? Down how much and right how much?
Would be right 2.
Okay, right 2. So x plus 2.
And then
Down
down 10.
10, yeah. Yep, I think you're right. Down 10. So y minus 10. Okay. So there you go. Alrighty. So sequence of transformations there. Okay. Last thing I want to look at, I'll hold off on the tries there, but I do want to look at one more thing here, and then we'll cut you loose on your homework, okay? So on the next page, page 130, okay? Investigating congruent segments and angles, okay? Congruence can refer to parts of figures as well as whole figures. So let me say that again. Congruence can refer to parts of figures as well as whole figures. So in other words, two angles are congruent if and only if one can be attained from the other by rigid motions, that is, by a sequence of reflections, translations, rotations. The same conditions are required for two segments to be congruent to each other. So here in example 3, determine which angles or segments are congruent. Describe transformations that can be used to verify congruence. So if you look here at letter A, okay, if you look at letter A, all of those angles, A, B, and C, are not congruent, right? You can see which ones are. A and C are congruent here. How could we determine if A and C are congruent angles here? What could we do? Well, it says here, the transformation that we could show as A to C is a translation. There is no transformation that maps angle B to either of the other angles. Okay? If you want to convince yourself quickly, visually, take a pencil and a piece of patty paper, right, and just copy angle A on your patty paper. Go and try and match it up to angle B. You'll see they don't quite match up. But if you go over to angle C, they do match up. Okay? So that's how you know that A and C are congruent there. And it'll be a translation. Okay? Likewise here for letter B, all right, if we copy AB, okay, we can then go and check. Is it congruent to EF? Nope. Is it congruent to DC? Yes. Okay? And so then how could you map it? You could do, reflection, it looks like, would get you what you want there. Reflecting AB, and then that would get you to CD. Okay? So we also want to be able to identify congruent parts as well as congruent figures and stuff like that. Okay? All right. Questions on any of that? Avery.
For the angles, could you find slope, like the slope of the other way?
I'd say so, especially when one side is the slope, all they have a slope of 0, then really it'd just be the slope of the ray there. Absolutely, you could check the slopes. If the angles are all like different, they're all turned and stuff like that too, it's a little bit harder to see that, but yeah. Okay. All right, very good. All right, so for your assignment then, don't forget you can work on your 10-mark assignment right now too if you would prefer, and do this homework at another time. It's up to you. Okay. Please make sure you are working on that 10-mark assignment. Your homework in the meantime, though, is going to start on page 131. Okay, and let's see here. I'll have you do numbers 1, 2, 4. 7, 8, 10, 12, 17, and I guess we'll stop there. Okay. Just those. 1, 2, 4, 7, 8, 10, 12, 17. Okay, it's a weird sequence there. So again, use this time now, please, to get started on either the homework or your 10 marks. All right? Please use this time now to get started on your homework or your 10 marks.